Okay, hi. So thanks for this opportunity to present my talk on multi-echo acquisition for fMRI sensitivity enhancement and data quality control, which is part of the symposium organized by Jean Chen and Ali Golestani. And I'm Benedikt Poser from Maastricht University, and feel free to contact me afterwards if you have any questions. So just start off with a quick overview. At the risk of boring some of you, I will revise how the signal decay upon bolt activation works. I think this is very important for understanding the motivations for multi-echo sampling. I will also go through how multi-echo sampling differs from single echo sampling, and then devote the majority of the talk to going into the reasons for why you want to do multi-echo. So first and foremost, for increasing bolt sensitivity, but this can come in different flavors or forms, for instance, by actually going into the separation of S0 and T2 star, using denoising techniques like the ICA or Tadana, which I will spend quite a bit of time on. And then I will round off with some practical aspects relating to the sampling and its trade-offs. Now, the fMRI signal depends on T2 star. This is why it's called the blood oxygenation level dependent signal. And what happens is that during activation, when the oxygenation level goes up, your signal decay will be somewhat slower than in the resting condition. So you have this slight difference between those two decay curves. It will follow a simple exponential decay. What happens in a regular single echo EPI sequence is that you have an RF pulse to excite the signal from one slice, and then you place an EPI readout at some reasonable choice of echo time, and the duration of this readout will depend on your matrix size, so the spatial resolution that you require. There is really not all that much to doing multi-echo. Again, you excite a signal using an RF pulse, but instead now of having a single echo readout, you have a rapid concatenation of, say, 3 to 5 now undersampled readouts in order to sample this decay curve at multiple times in a single shot. Now you have to use parallel imaging undersampling in order to get each of these readouts short enough to be able to put many of them together in concatenation. So what this looks like in practice is you excite the signal of one slice and you immediately get 5 echoes, excite the next slice, 5 echoes, next slice, 5 echoes, next slice, 5 echoes, next slice, 5 echoes. Now, this is all very well, but it actually gives you a pretty long TR, like in the regular 2D EPI sequence. Luckily, you can also add some SMS or multiband into the game. For instance, if you have a multiband factor of 2, you can excite 2 slices at once and get all the echoes for those 2 slices, and next, and next. And you see, using multiband factor of 2, you have already halved your TR as in a regular multiband acquisition. You can also play this for multiband 3. In this case, for the 12 slices, you can get them in only 2 shots, and correspondingly, your TR would be even shorter. This is some example data here from a 3 Tesla scanner at a fairly moderate resolution here, 5 echoes at a fairly reasonable range of echo times. So those were acquired with Grappa 3 in plane and multiband factor 3 in order to increase the temporal resolution. Having said all this, I just briefly want to give a bit of a history of multi-echo acquisition. From what I see, it really started off with a paper by Oliver Speck in 1998, where he suggested using multi-echo sampling for the separation of T2 star and S0, and I will show some of that. Very little later, Stefan Poser showed that multi-echo EPI can also be used to increase bolt sensitivity by combining the echoes together in some smarter ways. Again, a few years later, work by myself and later others performed the same thing again at 3 Tesla, again showing the gains in bolt sensitivity from doing multi-echo. You can push further in field strength, and even at 7 Tesla, we found that multi-echo EPI is beneficial. However, you will then find that you are pretty much limited in the spatial resolutions you can play out, bearing in mind that especially at high field, we typically want to go fast, go at very high resolution. Now, multi-echo is used quite widely for fMRI denoising, but also for simultaneous acquisitions of ASL and bolt, for example. More recently, and this, in my view, is a very big step, is the combination of multi-echo and multiband, which has really put multi-echo back into the game again and made it very competitive, since for a while the multiband had really taken over the field and people just wanted to go fast and threw away the idea of doing multi-echo sampling. But now the combination of the two is really super competitive. And I think there's a good place for multi-echo API to be used routinely. And that is a point I'm trying to make here. Okay, so what are the motivations for doing it? I've indicated that multi-echo API can be used for increasing bold sensitivity. It gives us multiple measurements of the bold signal at different echo times in one shot and at literally no cost, and allows you to recover the signal that's lost due to dropout. It allows you also to separate T2 star and S0 effects, which is nice because T2 star is the more direct measure of bold, and S0 is typically associated with motion, pulsation, scanner instability, etc. And there are a bunch of special applications that I will not go into today, such as dynamic distortion correction or special studies that look at the hemodynamic response and how it works. Okay, so first and foremost, motivation is that single echo fMRI is always a compromise. Now, I've explained the difference in signal decay between activation and rest, and you have to make a choice of echo time, which should ideally be dictated by what the value or the predominant value of your T2 star in the gray matter tissue is. So you want to sample at this point where the difference between activation and rest is the greatest. And if you plot this difference, you will get this bell-shaped curve here. You can also measure this experimentally, as done by Benedikt Poser many, many years ago at 1.5 Tesla using a visual stimulus. And you can actually see that this peak very clearly aligns with the predominant T2 star of 70 milliseconds. Now, the problem is that T2 star varies across the brain, and it does so quite a lot. So while in some voxels you might be wanting to use an echo time like this, there are other regions of the brain where your T2 star or apparent T2 star is a lot shorter, and you would want to be using a shorter echo time. So there is no single optimum echo time that adequately covers your bold response in the brain. Similarly, there are regions in the brain that are affected more strongly than others by signal loss or dropouts or signal voids, whatever you want to call them. And in particular, I'm talking about the regions here against near the auditory canals or the frontal brain regions where the signal dies off really, really rapidly, as you can see here from these 5 echo 3 Tesla data. So what happens is typically a very much shorter than optimal echo time is chosen, which means you're really sacrificing your sensitivity anywhere else to the point of the sensitivity dropping down to 60 or maybe 50% of what you would want to be at for the areas of the brain with a longer T2 star. Finally, as indicated, multi-echo gives you opportunity to separate task-related from artifactual signal changes because the bold effects happen in T2 star, whereas the artifacts happen in S0, which is the signal at echo time 0, whereas the T2 star, as said, is the rate at which the signal then decays. So if you have a multi-echo acquisition, you can perform a fit to separate out the S0 and the T2 star. And for this visual stimulus here in the work by Oliver Speck many years ago, you see very nicely that the T2 star time course follows the visual activation, whereas the S0 would capture anything else, which is pulsation, motion, or slow drift, or heating in the scanner here in this case. So this works, and it's been shown very early on. But okay then, so we have a multi-echo sequence, we acquire some multi-echo data. What do we now do with this data in practice? Now the easy way is just combine the echoes together in a more or less smart way. If you merge all the echoes into one time series, you have only one time series to deal with, and you can proceed with a standard analysis. So that sounds very handy. In principle, of course, nothing would stop you from performing separate fMRI analysis on each of the echo time courses separately, and then going in and picking the best Z-score or T-score for each of the voxels. Now, you can do that, but I think it doesn't take much to realize that this is suboptimal because we should always exploit the benefits of signal averaging. So this is what we're going to look at here. Simplest thing in a way is to perform echo summation with equal weights. So you just take all the echoes as they come in from the scanner, you average them together or sum them together, and you will find that this improves sensitivity, at least up to a certain point. And this was simulated and shown again by very early work by Poser, that pretty much whatever you do, you will have some sensitivity gain that is in the positive. But if you start adding too many late echoes, you'll also find that the sensitivity will drop again because you start adding too much noise. In practice, you will not encounter this. In practice, summation is a perfectly valid way of doing it. I'm just pointing out that there is a risk of adding in noise for later echoes. What you really want to be doing then is have a weighted combination that is adaptive with voxel-wise weights. And you want to weight the echoes according to how much the echo times and pixels contribute to the bulk sensitivity. So in practice, that means if you have a red voxel here in the frontal region where the signal decays fast and the bulk sensitivity curves is weighted towards the shorter echo times, you want to give more weights to the shorter echoes, the early echoes. Whereas if you have a blue pixel, for example, which has a brain region of slow signal decay, you would also want to be putting more weight on the later echoes. So this is then some typical results you might get if you do this. Here's a single echo at a typical echo time of 30 milliseconds at 3 Tesla. You see again these sort of big holes around the auditory cortex in the frontal regions. And if you have a weighted summation of 5 echoes, you see how these areas are very nicely filled in with basically no dropout being visible here. In terms of the relative performance of these methods, this goes back to early work by myself at 3 Tesla here. We found that CNR weighting is best for task fMRI at 3 Tesla. By CNR weighting, I mean basically determining the temporal signal to noise of each echo in order to compute how much does each echo effectively contribute, and then weight the time series of the echoes accordingly. Result, in a nutshell, is basically that whatever you do, you will always win but never lose. But we found that CNR weighting is somewhat better than using a T2 star weighted approach or simply summing them together. So there's always a bit more gain if you do this TSNR based or CNR based weighting than the other choices, but the main point is you will always gain some. At 7 Tesla, it was a little simpler, basically because all the echo times contribute similarly, at least for this experiment, which we performed at those echo times here. Similar sensitivity of each echo basically meant there was no additional benefit of having any fancy summation scheme, so just clumping them together into a simple sum was perfectly adequate. Okay, now having said all this, you might provocatively argue that echo weighting might have become redundant in some way given the availability of much more advanced multi-echo denoising options, for instance, the multi-echo ICA Tidana that I'm about to talk about. But this is actually not true for real-time applications like neurofeedback, for instance, where you very rapidly have to perform data analysis on the images that come in, compute your next feedback, and so on. So you don't really have time for anything too fancy, and your data must be maximally good. So here's really a good case for optimizing your bulk sensitivity in real time based on the data as they come in without doing anything fancy like this processing. Now, this is a slide here from Stefan Hoeneß, and this is actually his results shown at the Benedikt Poser meeting last year. So he again looked at different ways of combining the echoes on the fly using a weighting by pre-scan T2 star or TSNR maps versus real-time computed T2 star. And again, very much in line with other work, he observed 20 to 100% sensitivity gain for all the methods compared to a typical echo time. Very nice. Okay, so there are smarter ways, though, than just combining the echoes together. And that is really exploiting what the echoes tell you. And that is a heck of a lot. And here I'm now talking about multi-echo ICA denoising and the time-dependent echo analysis, as was proposed by Prantik Kundu. Now, the echo time dependence of changes induced by T2 star or S0 is fundamentally different. Now, if we look at T2 star induced signal changes, so changes in the decay rate, and we look at the relative signal changes per echo time, we see this bell-shaped curve that I showed you earlier. Another interesting way to look at it, however, is to express this as a relative signal change, which is basically the delta S as a function of echo time over the signal as a function of echo time. And what you then observe is that you have a linear dependence of this relative signal change on echo time. So this is for changes in T2 star. This is not so for any signal changes induced by S0. You can go through the same game again, but you will end up seeing is you have a flat echo time dependence or low echo time dependence of any signal changes that happen in the S node component. And this is effectively what Quantic showed in this work in 2011, and which is the key, or understanding which is the key for separating changes that are related to activation and changes that are related to nuisance, like drift, motion, and fluctuation. So again, coming back to this work by Oliver Speck here, the simplest thing you can do is then say, okay, well, we have the multi-echo data, we simply fit it, we separate T2 star and S node, we have a plot of what's probably signal changes due to drift and motion, pulsation, etc., and we get the T2 star courses and courses as a representative metric for our activation. By the way, this also allows for doing triggered non-steady state fMRI. For instance, in brainstem, this might be advantageous using triggering when you're no longer in a steady state because your TR varies from shot to shot. And this was some work by Florian Weissner about 10 years ago. You can also do the T2 star calculation on multi-echo data now at higher field strength of 3 Tesla. Some examples are shown here, where I compared different weighting schemes, like CNR weighting, bold weighting, versus fitted T2 star, and this also worked very well. Looking at the S0 components or signal components extracted by melodic, which have an S0 dependence, they mainly show artifact breathing and flow. You can basically see that by just eyeballing them here. And the question, of course, being asked, how are these components suitable filters for data cleaning? Well, of course they are. And coming back to the multi-echo denoising by Pante Kundu again, this is exactly what's at the core of it. The way that he proposed for doing this was to spatially concatenate the echoes together, say 3 echoes in this case, and then perform an ICA to model the TE dependence of the component, or to extract components and then look at them to what extent they show a T2 star-like behavior or a change in S node-like behavior. So how this works is that he took the knowledge that the signal decay is pretty much non-exponential. He combined it with the TE dependence model proposed by Ravi Mann in 1994. And then you can arrive at 2 expressions that try to capture how the signal changes, either as a function of S node or as a function of T2 star, R2 star, as a function of echo time. So you can obtain your components by doing the ICA on the concatenated echoes. And then for each of the components, you determine the goodness of fit to either this model or that model. And then you can get a measure of how bold-like a component is. For instance, this component looks very bold-like because it nicely shows the resting state network popping up. Or you can get a artifact-like component characterized by the rho, bold-like is kappa, which looks very much like motion because you have this sort of activations around the skull. Okay, now how do you do this in practice? It's very well described in Pantik's paper, and I don't really have too much time to go into this here, but I do really want to point out that there has been a lot of work going on recently in making this method very accessible now. Originally, there were scripts provided by Pantik himself that were AVNI-based and really intertwined with AVNI and very hard to actually apply by anyone who wasn't familiar with AVNI. But the more recent effort of the Vedana community has been absolutely fabulous, and it's like super well documented. So I've even gone into building a sort of a bits compliance pipeline, which people are able to download and use. Now, this really makes it accessible for everybody. It's open source, it's Python, it's extremely well documented, and it has a lot of background information, way more than I can capture in this talk here. And it has links to very useful resources as well, like other papers that have used multi-echo or protocols that you could use for examples. So with this, I should really give very big kudos to this Vedana community. And I highlight Elizabeth Dupré here, who's the BDFL of this project. And it's really amazing what they've put together in the last couple of years. Okay, getting closer to wrapping up, I want to go a little bit into the practical limitations. Now, multi-echo is at a free lunch. So far sounded like as though if it was, to a large degree it is. However, there are some limitations that you have to bear in mind, of course. Now, the first one is spatial resolution. The duration of each of the EPI readouts increases with the resolution linearly, but we also need to be able to sample the fold response at reasonable echo times. So we can't just push this out endlessly and sample it like echo times. It would make our TR long, and it would also sacrifice our sensitivity. Now, looking at practical examples without going into the details of matrix size and bandwidth and so on, I would say if you have a sort of a resolution of 2.5 millimeter voxels at 3 Tesla, you can get 3 echoes, factor 2 in plane resolution. 3 millimeters, maybe you can get 4 echoes, 3.5 millimeters, so it's a bit unfancy, low resolution. You can probably squeeze 5 echoes easily with a bit more acceleration here. Similarly, considerations apply at 7 Tesla. Now, so this is for the spatial resolutions that you can squeeze in order to sample your echoes at a reasonable echo time. But what about temporal resolution? You do want to use some multiband in order to deal with temporal resolution. However, you have to bear in mind that your total acceleration capability of your RF call is limited to, say, like a combined multi-echo, like a combined grappa factor or sense factor and multiband factor, reaching no more than 8 or 9. 9 is already very pushy. I would even say 8 is already on the pushy side. Because you have to bear in mind that even multiband, it is just a form of parallel imaging. It's no magic involved there. It is equally limiting as your in-plane acceleration. So what does this mean in practice? For acquisitions that have a factor 2 in plane, that basically means you can push to multiband 4. If you have a factor 3 in plane, you are probably limited to multiband 2, maximally 3. And again, similar considerations apply 7 Tesla, but then you're anyway more limited because you're not able to use anything close to the spatial resolutions most people want to be using at 7 Tesla these days. So think about that and be careful. Don't be too pushy, but for those protocols here at 3 Tesla, you can get very nice protocols with a TR well below 1.5 seconds at a pretty decent resolution quite easily. To conclude with some final remarks, I would argue that multi-echo EPI by itself can improve your bolt sensitivity in the whole brain at effectively no cost. You can remove all the compromises of single echo fMRI, at least in the context of normal neuroscientific studies. You can even reduce your signal voids. You can even reduce the distortions, sort of as a byproduct of the fact that you have to do parallel imaging acceleration. So each readout becomes shorter, there's fewer distortions. And there are different ways of combining the echoes together. Most importantly, however, there's a very powerful way of processing and data cleaning offered by the Tidana approach. And in any case, even though you require multi-echo data, in the end, you end up with one single combined time series, which you can just put through standard analysis. So all the pre-processing can effectively be put in a black box that is well tuned, and a regular user would not have to go through any additional trouble of using multi-echo EPI. The sampling is easily combined with any 2D or 3D EPI, multiband EPI, or spiral sequences. I just want to say that for completeness here. But the typical case, of course, is to have a 2D multiband EPI, which you now run in multi-echo mode. Now, the take-home message should remain, however, that with modern hardware, so the good scanners we have, the very high quality of grappa sense and multiband parallel imaging that we have now available, and now not least the availability of really excellent open source tools, I really do not see a good reason for not using multi-echo at 3 Tesla for a typical neuroscience study. So with this, I would like to thank you for attention, and I really urge you to go to the website of the Tidana and look at the wonderful resources this team has put together. Thank you very much.